This is part 2 in the proof that context-free grammars and non-deterministic push-down automata have the same expressive power. Context-free grammars and non-deterministic push-down automata can define the same exact class of languages. A language is context-free if and only if some non-deterministic push-down automaton recognizes it. In the previous video, we did part 1 of the proof. In other words, given a context-free grammar, we showed how to construct a push-down automaton that recognized the same language. In this video, we're going to do part 2 of the proof, going in the other direction. Given a push-down automaton, show that there is a context-free grammar that recognizes the same set of strings. We're going to do that by showing how to construct that context-free grammar given a push-down automaton. So in this half of the proof, we are given a push-down automaton and we need to construct an equivalent context-free grammar. Buckle your seatbelts. This part of the proof is a little tricky and a little technical, but let's go through it slowly. Okay, keep in mind where we are. We're given a push-down automaton, and our goal is to build a context-free grammar from that push-down automaton that recognizes the same set of strings. So we're going to do this in 2 steps. First of all, we're going to simplify the push-down automaton, and then we're going to show how to build the context-free grammar. In the context-free grammar that we build, we're going to have a bunch of states. We're going to have a bunch of non-terminals. Here is the push-down automaton. It's got a bunch of states in it. It's got a starting state. It's got a bunch of except states. When we simplify it, it'll only have one, but it's got a bunch of states. Okay? And we're going to build a grammar. And for every pair of states in the push-down automaton, we're going to create a single unique non-terminal symbol in our grammar. Okay, so we're going to create a bunch of symbols bunch of non-terminal symbols in our grammar. So for example, for P and Q, we'll generate a state, and we're going to call it, we'll generate a non-terminal, and we're going to call it APQ. We'll also create a non-terminal for QP. So I don't show that, and I probably should, but in addition to APQ, we'll have a non-terminal called AQP. The starting symbol for our grammar will be the non-terminal with the name AQ0 QAccept, where, in other words, for the pair of states Q0 and the accept state, we'll create a non-terminal for those 2 states, and that non-terminal will function as the starting symbol in our grammar. Okay, our first step is to simplify our push-down automaton. We want only one accept state, so we're going to modify our push-down automaton by adding a new accept state, which we'll call QAccept, and we'll add additional transitions to our push-down automaton that go from every one of the previous accepting states to this new accepting state. They don't do anything. We'll label them with epsilon, epsilon, epsilon. Okay, so this is our new accepting state. Then we want to make sure that the PDA empties its stack before accepting. Okay, so what we're going to do is we're going to create a new starting state, Q0, and what it's going to do is push onto the stack a $sign without reading any inputs. So if this was our previous starting state, we've got a new starting state that pushes $sign, where $, is some symbol that's not otherwise used in the stack alphabet. And then we're going to take that previous accept state and add yet another state, and now this is our accept state, and this state here is no longer an accept state, and instead we add transitions that will pop anything left on the state. So for every element of the stack alphabet besides $, we have an edge that does nothing but pop that symbol from the stack. And we have another transition that finally pops the $sign from the stack and moves us to our accepting state. And this is the last accept state we'll have. This is our accepting state. So now we've got a pushdown automaton that will empty its stack for sure. In order to reach the accepting state, it must empty its stack. And you can see, I think, that this machine will accept the same set of strings as we started with, the machine we start with. These modifications to simplify the machine won't change the nature of the machine. We have a couple more simplifications to do as well. Okay, the next simplification we want to do is to make sure that every transition in our pushdown automaton either pushes something onto the stack or pops something from the stack, but does not do both. Okay? So we need to show how to modify transitions that both pop and push, as well as modify transitions that don't do either. So first, if we have a transition that pops an X and pushes a Y, we need to introduce a new state into our pushdown automaton that first pops X and then immediately pushes Y. So this transition pops, this one pushes. If we have a transition that neither pops nor pushes, what we'll do is we'll create a new symbol and add it to our stack alphabet. Okay, a symbol that's not used anywhere else. Let's call it Z, a dummy symbol, and we're going to add it to the stack alphabet. And then we're going to replace this transition with two transitions and create a new state for this purpose. And what we're going to do is we're going to push this dummy symbol as we scan A, or epsilon perhaps, whatever we scan on the input, either some symbol or not. We're going to push Z, and then immediately, without scanning the input, we're going to pop that same symbol. So now every transition either pushes or pops onto the stack, but it does not do both. And we start with an empty stack, as every pushdown automaton does when it begins execution, and more importantly, we always end with an empty stack. Now let's imagine we're programming a pushdown automaton. Imagine as a programmer you've got a stack and you want to write a subroutine to do something. Well, typically what you want to do is leave the bottom of the stack alone. You may use the stack to push some temporary data that you're going to be using for your subroutine, and then later you'll pop that. But the idea is you want to leave the stack the same way you found it. Okay, so we have this concept of doing some computation in such a way that the stack is not modified. We may use the stack, we might push some stuff onto the stack, but whatever we push, we pop. And we don't go down deep in the stack. If something's already on the stack, we don't touch it. We don't read it, we don't remove it. Okay? So that sort of a computation, if you started it with an empty stack and you finished it with an empty stack, you would finish it with an empty stack and it would work just fine. Since it doesn't look below the current top of the stack, it wouldn't matter whether the stack was empty or contained some other stuff. So it doesn't touch whatever's on the stack. Okay, so here's an example computation that behaves like that. It does some pushing, and regardless of what else is on the stack, symbolized by these black hash marks, it can push a few things and it can pop a few things and push and pop and push and pop, but ultimately it ends up popping and leaves the stack exactly the way it finds it. It doesn't go deep down into the stack. It doesn't go down into the stack. The first thing is a push, and the last thing is a pop of the thing at the top of the stack. Okay, so during this computation, the stack may grow and it may shrink, but since we never touch the stuff that's black here, we never go below that level, the level that we start with in the computation. So this is sort of a graph of what happens to the stack during the computation. Okay. The first thing we have to do is push. Since every transition either pushes or pops, we can't pop because we can't look below this dotted line. This graph is showing the stack height, okay, as a function of time as we take transitions. Okay. The first thing is always, it must be a push. Okay. And so we do some stuff. The stack grows and grows and shrinks and grows. It may go all the way back to 0, or back to where it started, I should say. Okay, it may go back to where it started at the beginning of the computation, but it won't go below that dotted line. Or it may never go back there until it finally ends. But at the end, the last thing will always be a pop, because it can't be a push. It has to leave the stack exactly the way it finds it. So nothing down below here is ever touched. Here's the main idea in this step of the proof, in this half of the proof. Consider two states, P and Q, in the pushdown automaton. And ask yourself, could we go from state P to state Q without touching the stack? That is, without going negative in the stack, without going below the dotted line, so to speak. If we had an empty stack, could we go from P to Q and end with an empty stack? And our question is, what strings would do that? Okay, which strings would take us from state P to state Q in our pushdown automaton without needing to look at what's already on the stack by the time we reach P? What strings would do that? Starting with an empty stack, can we go from P to Q and end up with an empty stack? Or if something was on the stack, if there were some things on the stack, they would never be looked at. They would never be touched. Okay? What strings would do that, would take us from P to Q? And the idea is that we're going to construct a grammar. Remember, we're trying to construct a context-free grammar that does exactly what this pushdown automaton does. It recognizes exactly the same strings that this pushdown automaton does. So the question is, can we build a grammar that way? In the grammar that we build, okay, we're going to have a non-terminal, okay, and we'll call it a PQ, where P is a state and Q is a state in the pushdown automaton. So for every pair of states, for every ordered pair of states in the pushdown automaton, we'll have a corresponding non-terminal. And that non-terminal, which we'll give this name 2, will generate exactly those strings. That is, it will generate exactly the strings that would take us from state P in the pushdown automaton to state Q on an empty stack without modifying the empty stack, and would end up with an empty stack. So to say it again, we're going to build a grammar, and for every pair of states in the pushdown automaton, we're going to create a non-terminal. And that non-terminal will generate exactly those strings that would take our pushdown automaton from state P to state Q on an empty stack and end with an empty stack. Let's imagine going from state P to state Q. We're going to start with an empty stack and we're going to end with an empty stack. Or equivalently, we're going to start with a stack that has some stuff on it and we're never going to look at that stuff. We're going to end with the same stack. How can we get from P to Q? Well, we have to take a transition to some other state, okay? And eventually we have to get to Q. Every transition either pushes or pops. That first transition that we take cannot be a pop, right? Because we are saying that we're getting from P to Q without modifying what's down here on the stack. We're starting, or equivalently, we're starting with an empty stack and we're not going, and we can't pop an empty stack. So the first transition must be a push. And the last transition, likewise, has to be a pop. Okay? And so we're pushing something onto the stack, and the stack height changes, goes up and down. Eventually we pop that symbol. Okay, so in this case, we're assuming that we're going to look at two cases. And in this case, we're pushing a symbol, and the symbol that we're popping is the exact same symbol. So here the stack height never goes down to 0. Okay, if you look carefully at my little chart here, it never goes back to this level. Okay, we don't pop Z until the very last transition. The stack height is always 1 or greater during the intermediate stages. So let's say we go from P and our push takes us to some state R. And we do some stuff, and our last transition takes us from state S to state Q. So what strings can be generated along that path? Okay, well, whatever this input symbol is here on this transition, that must be the first string, symbol in the string. And whatever symbol is accepted here, whatever input symbol is scanned here, has to be the last symbol. These can be epsilon. Of course, if this is epsilon, we wouldn't have anything here. And now we ask ourselves, since we've pushed a Z onto the stack here, and we're going to pop that same Z off the stack here, we're never going to look at that Z. So we're going to get from R to S without looking below that level. So we've increased the size of the stack by 1 by putting the Z on it, and we're never going to look at that Z. So we're going from R to S. What strings could take us from R to S on an empty stack and end with an empty stack? Or what strings could take us from R to S without looking below the current level of the stack? Okay, well, fortunately, we have these non-terminals to do exactly that. So what could take us from R to S is just defined by the non-terminal A sub RS. So to get from P to Q, we need to scan an A and then get from R to S without touching the stack or leaving the stack as we found it, and then we need to scan a B. So we're going to add to our context-free grammar this rule. We're building a context-free grammar from the PDA, so we can add this rule to our PDA. This rule will generate exactly the strings that would take us from P to Q, where we push a Z, do some stuff, and then finally pop the Z. Those are all the strings that would do that. We just described how to get from P to Q, where we started by pushing something and then popping the same thing. But it's also possible that we can get from P to Q, and the first push we do is not the same pop we do. In other words, we push a symbol here, but it's not the symbol we pop on the last transition. What that means is that somewhere along this computation, the stack goes back to 0. Okay, if we start with an empty stack, we start by pushing W onto it, some symbol W, and we do some computation, and at some point we get back to an empty stack. We pop the W, and then we do some other computation, and some more stuff gets pushed, and the transition right before Q will pop something else, Z, a different symbol. So in this scenario, the stack does go down to 0 between P and Q. So what strings can be generated by following that path? Well, we've got the strings that take us from P to R. Okay? No, we're going from an empty stack here to an empty stack there. Okay? And then we go from R to Q, from an empty stack to an empty stack. So the strings that take us from P to Q consist of the strings that take us from P to R and from R to Q. And we have non-terminals to describe those strings. This rule will generate exactly the strings that we're after. To get from P to Q, from state P to state Q in the pushdown automaton, we could go from state P to state R, end up with an empty stack, and then go from R to Q, again from an empty stack, ending with an empty stack. So now let's repeat the recipe for constructing our context-free grammar. We're given a push-down automaton and we've simplified it. We've made sure that we have exactly one start state and one accept state, and that the stack is emptied before we reach the accept state, and that every transition either pushes or pops. Now we build our context-free grammar. On this slide, I'm going to talk about the first situation of rules we add to our context-free grammar, and on the next slide, I'll talk about the other rule that we add. So, to repeat what we said earlier, if we've got this pattern in our push-down automaton, then we're going to add this rule. In other words, if we have edges that go from P to R, pushing a symbol, and from S to Q, popping that same symbol, then if it's possible to get from R to S on an empty stack without touching the stack, in other words, only pushing and popping but never popping down in below the where the stack currently is, whatever strings that will take us from R to S can be used to get us from P to Q without touching the stack. So if we could get from R to S without touching the stack, then we need a grammar rule that will allow us to get from P to Q without touching the stack, without going negative in the stack. So when we see this pattern of these rules, we need to add a new rule to our context-free grammar. And the grammar rule has the left-hand side of a non-terminal A, P, Q, and the right-hand side is the symbol, the input symbol A, possibly epsilon, whatever labels the push edge, and a non-terminal to get us from R to S, and the input symbol that labels the pop transition. Here's a more formal way to say that exact same thing. For every set of states, P, Q, R, and S, in the push-down automaton, such that, and this is essentially saying that we've got a push edge from P to R, okay? Input symbol A, it reads 0 things off the stack, it pops nothing, but pushes T, and the transition from S to Q pops a T, and this is an epsilon, not a T, it pushes nothing, then we add this rule to the grammar that we're building. A, P, Q goes to A, R, big A, R, S, B. Now the other thing we need to do is add the other sort of rule to our context-free grammar. If we have a way to get from state P to state R that doesn't touch the stack, okay, then we've got a non-terminal symbol in our grammar, A, P, R, and that will expand to all the strings that will take us from P to R without touching the stack. And if we've got a way to get from R to Q without touching the stack, well, some strings will take us from R to Q without going negative in the stack, without touching the stack. In other words, some strings will take our PDA from state R to state Q on an empty stack and leaving it with an empty stack. And those strings, the exact same set of strings, is generated by the non-terminal A, R, Q. Well, now we have a way to get from P to Q on an empty stack. We have a new way to get from P to Q without touching the stack. So we need to add this rule down here, A, P, Q, and we go through R, A, P to R, and then from R to Q. So for every set of 3 states, for every possible combination of 3 states in our push-down automaton, we need to add a rule that will tell us that we can get from P to Q if we can get from P to R on an empty stack, and we can get from R to Q on an empty stack. Finally, we have a couple of bookkeeping details to take care of. There's a trivial way to get from any state to itself without touching the stack, namely the string epsilon. That will take our push-down automaton from a state P to that very same state without pushing or popping the stack. So we need to add a rule to our grammar for every state P that looks like this. Okay, if the pushdown automaton accepts some string, then there's a way to go from the starting state to the accept state that does not modify the stack, because our pushdown automaton starts with an empty stack and it ends with an empty stack. So we can go from Q0 to QAccept, and the set of strings that will take us from Q0 on an empty stack to QAccept with an empty stack is exactly the set of strings that the pushdown automaton recognizes. So the grammar we seek should generate exactly the same strings. So we need our start state in our context-free grammar to be the non-terminal A, Q0, QAccept. So to summarize, we've shown how to go both ways. In part 1, we showed how to take a context-free grammar and build an equivalent pushdown automaton that recognizes the same language. In this part of the proof, we've shown how to take a pushdown automaton and produce a context-free grammar that generates the same set of strings. So we've shown that both context-free grammars and pushdown automata have the same power. They can accept and recognize the same class of languages.